Suppose that the distance of fly balls hit to the outfield in baseball is normally distributed with a mean of 229 feet and standard deviation of 64 feet. Now, we're going to look again at two cases, one where we look at individual fly balls, and another where we look at a sample, a collection of fly balls and look at the average distance they travel. Okay, so for the first one, we're ultimately asking 27% of fly balls are hit further than what distance? So first, we want to look at the distribution. Now, we're told that the distance the fly balls are hit are normally distributed. If we put all those distances together, we have a normal distribution. Okay. The mean is 229 feet, and we have a standard deviation of 64 feet. So here we're looking at individual values, right? So we're looking at symbolically the x's, okay? So we're looking at individual fly balls. We're looking at individuals in the population. And so we just need the population mean, which we are told is 229 feet, and the population standard deviation of 64 feet. Okay? And so that's what goes here. No tricks for this first bit. So our mean and our standard deviation. Okay, because again, we're just looking at the basic probability or population distribution here. Okay. Now, once we have that, we need to list the z-scores needed to calculate this result. Now, to do that, we first need to really understand what's going on here. Okay. So we have a normal distribution. So we have that lovely bell curve. But what's it actually asking? It's not asking for a probability, right? It's saying 27% of fly balls are hit further than what distance? So it's giving us a probability, and it wants us to find the x value that corresponds to that probability. So let's see. So our mean is what, 229? And we want to find 27% are hit further than what distance? So we're looking for the top 27%. Okay, that's our probability in the upper tail because we want it further than what distance. And then we're looking for what is this value here. Okay. So remember that when we're going between an x value and a probability, we always have to go to the z value first, right? So we could go this way using z equals x minus mu over sigma. And then we could go this way using the p-norm function in R. Okay, but in this case, we aren't given the x value. We are given the probability. So we want to go backwards. We want to start from the probability and go to the z value. And for that, we use the q-norm function because we already know the p. P is the probability. And then once we have the z, we can use the z to get the x using the formula x equals mu plus z sigma. Okay? So we are going to take the red path this time because we are told what the probability is and we are looking for the value, right? 27% of fly balls, 25%, that's our probability. 27% of fly balls are hit further than what distance? The distance is the x that we're looking for. It's the value in the population. Okay? So to find the z-scores, we're going to need to use that q-norm function. Okay? So let's go to our notebook. And we'll have q-norm. Q equals, or I'm sorry, P. P equals our probability is 0.27 because we wanted that 27%. And when we shaded it in, we wanted the upper tail, not the lower tail, right? So we're going to set lower tail equal to false, right? Because we are shading in the upper tail over here, not the lower tail. So let's set that equal to our z-value. Let's print out that z so we can see it. Okay, so there's our z-value, 0.6128. Okay, so that goes here. And let's see, what do we say these were? Let me blow that up a little bit. 229 feet and 64 feet. Okay, that was our mean and our standard deviation. Now our z-value, what we just calculated with that q-norm function, is 0.6128. So now we're ready to answer the last question. Okay, so in other words, we've made this first step on this red path. We've done the q-norm, we have the z-value. Now we just need to make that last step using this formula. Okay, so for this, our x is going to be, and we're going to have our mu x, let's be specific since we're going to have multiple x values, plus our z times our sigma x. So for us, that's going to be 229 plus the z-value we just got with the q-norm function, right, times our sigma x, which is 64. So let's plug that into our notebook, and we'll have our answer for the last part of part 1. Okay. So mean of 229 plus our z-score. And since I stored it in the variable z, I could just type in z. If you want, you could copy and paste or put an approximation. But I think it's easier to follow if we just put z. Times our standard deviation, which was 64. And we see that we get 268.22. Okay, so copy and paste that. So that means 27% of fly balls are hit further than 268.22 feet. Okay? All right, so part 2. We're doing almost the same thing, but now we're looking at a sample of 59 fly balls and seeing, looking at the average of that sample. Now, instead of looking at just one fly ball, we want 27% of samples of 59 fly balls are hit an average of more than what distance. Okay, so again, we're going to need our central limit theorem here, right? Because now we're not dealing with a single value, we're dealing with a sample of values. And we're looking at the x bars, the averages of those samples. So we will need the mean of those sample averages, which is the same as the mean of the population, which is 229. And then the standard deviation of those sample averages, which according to the central limit theorem is the population standard deviation divided by the square root of the sample size. In our case, that's 11 is the population standard deviation over the square root of 59. Okay, so let's throw that into the notebook so we could get the mean and then the standard deviation. So notebook. So I'm going to take that 11, that is my population standard deviation, and divide by the square root of the sample size, which is 59. And we get 1.432 about. So that's going to be the standard deviation of sample means. So let's copy that. So that's our standard deviation, 1.43. And then the mean is still 229. The mean doesn't change when we're looking at samples, the collection of sample means instead of just the individual fly balls. Okay? Okay, now we want to calculate the z-score. We're going to do it almost the same way as we did in part 1, but we're going to use the mean and standard deviation that we have here for this distribution of samples. Okay? So same idea. By the central limit theorem, all those sample means are normally distributed. And we want the top 27% of them. Okay, we want to know what is this value? What is this value so that only 27% of fly balls of averages of the samples are bigger. Okay, only 27% of sample averages are bigger. So, same idea. We are given a probability. We want to take that to z using the Q norm. And then from z, we're going to take it to x bar, the sample mean that has only 27% of sample means bigger than it. Okay, and we're going to do that with z equals the distribution mean. I'm sorry, x equals. So the value x bar equals the distribution mean plus z times the distribution standard deviation. Okay? So let's first find that Q norm. Okay? So this will be our z value for this case. Q norm. The probability is 27%, or 0.27, and we are taking the upper tail, so lower tail will be false. And let's write z there so we can see what we actually get. So 0.6128. You'll notice that's the same answer that we got for part 1. And that's on an accident. Notice we haven't used any of this information. We haven't used this mean and standard deviation when we get the z-score. All we are looking at is what's the z value so that 27% of z's are bigger than it, right? And since it's the same standard normal distribution, it's the same z value. But now we're going to take that z and we're going to do something different with it. We're going to use the same formula, but with this mean and this standard deviation. Okay, so we're going to use that mu x bar plus z sigma x bar. So we're going to have our mu, 229, plus our z, and I stored z in a variable, so I'll just use that variable. But that's our 0.6128 right here. Okay, and then times our standard deviation. So this is our standard deviation of sample mean. So that's the one I'm going to use. I didn't store it in a variable, so I'm just going to copy and paste it. Okay. Run that. I get 229.877. Let's copy and paste that, and that's going to be our final answer here, which means 27% of samples of 59 fly balls are hit an average of more than 229.8776 feet. Okay, what that means is if you were to look at a randomly generated collection of 59 fly balls and look at their distances and average all those distances together, there's a 27% chance that that average you get will be more than 229.877 feet. Okay, so let's submit it. Okay, we got a couple errors here, so let's see what's going on here. This is a good learning experience. Let's see what happened. So if we go back here, let's see. Oh, you probably caught this while you were reading. I think I got this from a previous problem. Our population standard deviation isn't 11. Okay, it's not 11. Our population standard deviation is 64. So this is one of the utilities about using MyOpenMath, is you get to see exactly where you first go wrong. So I could see, oh, gee, I went wrong at my standard deviation. And because I had that wrong, I got the wrong final answer here. Now the z-score is the same because remember it didn't rely on the standard deviation. We didn't use the standard deviation to find that z-score. So let's make that correction. So the population standard deviation is 64, not 11. Run that. So we get 8.332. So that's going to change things a little bit. So let me throw that in first. So that's our new answer there. Okay. And then we're going to use that standard deviation to fix our final answer here. So instead of 1.43, it's going to be that 8.332. Run that, and we get a different answer here. So let's copy and paste that. Okay. Let's submit it. Okay, now we got it all right. Okay.